Okay, so I already recorded this video, but it turns out my thing ran out of memory, and I have to do this again. So this really sucks. Okay, so let's talk about Serre, Tate's. So there's Neron-Ogg-Shafarevich criterion. All right, and this is for good reduction of an abelian variety. So I'm going to talk about how the properties of the l-adic Galois representation determine how the reduction type, or at least the first part of a good okay, so let me just say the motto here. So it's about how the reduction type is related to the Galois representation. So it's that the reduction type at a place, okay, is related to, okay, I'll do that. So it's not an if and only if, the Galois representation. Okay. All right. This is the idea. Let me give some setup here. And I'm going to do a local version. The local version and the global version are related to each other. So we're going to take K over QP. This is going to be an algebraic extension. We're going to take K to be the residue field. The characteristic here is going to be P. R, of course, right? R is going to be the ring of integers. And then we're going to take AK, so this is going to be an abelian variety over K. Okay. All right, and so let me just remind you that an abelian variety is projective connected algebraic group, automatically commutative. The connected part, I just want to remember, because sometimes we forget about this connected part. That's important. Okay, for this in particular, we're going to use this later. All right, and so let me just remind you what good reduction is. Okay, so A over K has good reduction. This is an abelian variety over K, has good reduction. If and only if, so this is the local case, there exists some A over R, an abelian scheme, with A eta isomorphic to, so we don't have to specify the isomorphism, but there's an isomorphism with AK. Okay, so that this thing exists. Okay, so that's what it means to be good reduction. So in particular, this is like smooth and proper, and I guess you could do this in versions where you don't necessarily have an abelian variety or abelian scheme. Okay, so some notation. So let me do some representation theoretic notation. Okay, so first recall. So let's do this. So AM. Right, so this is, so actually let me do it like this. If C, crap. So if C is an abelian variety over L, so sometimes this denotes the group scheme, but for this time, okay, we'll sometimes denote it as a group scheme, but I'm going to abusively have this be the L bar M torsion points. Okay, so that's what we're going to do, and I'm going to use it on the special fiber and the generic fiber of some models. So we're going to do it over several fields. Okay, and so recall. Okay, so that this is what we have. So now I'm going to talk about inertia, what this means for Galois representation. So, so if we take our absolute Galois group, okay, I should have talked about this last part first. There's this specialization map. In the kernel of the specialization map, this is inertia. And so we'll just call this I sometimes. So we have this sequence here, this like homotopy sequence. So we say, so given rho from this, the absolute Galois group of this field to some automorphism of some object. I guess it doesn't need to be that, but it just can be anything, right? Then rho is unramified if and only if rho of the inertia is 1. So this is saying that inertia acts trivially. Okay. Okay, so this is what we have in the local situation. Okay, so for the global situation, so just a little bit about global conversion here. So let's take L to be a global field. Okay, and we'll take V, a place of L, so a finite place, and then we'll take V bar to be a place over V, so V bar is a place of L bar. Okay, and then what we can do is we get a similar sequence, so this is V bar over V. This is the stabilizer of with respect to GL, that absolute Galois group of V bar, and then this goes to G kappa V bar over kappa V. So this is the residue field, and then the kernel of this map is called the inertia group, and this thing here is also the absolute Galois group of the localization. Since this is in here, this thing embeds in, so this thing goes inside G of L. Okay. So this is what we have here, and so given a global representation, so given rho from, let's say, GL to the automorphism of X, right? We say rho is unramified at V. By the way, these are defined up to conjugation. The thing above it is really what. So if you change the lift, you're going to change these things by a conjugation. So, okay, so this thing's unramified at V if and only if, so rho restricted to GLV is unramified. Okay, that's the definition. And then we say that, so given A over L, some abelian variety. All right, and then we could also do this without abelian varieties, but we say that A over L has good reduction if and only if ALV does. Let's say, good reduction at V. Okay, so V is a place. So we have good reduction at V. Okay, so this is what we have. So we can convert between these two results, and so the global thing turns into the local thing, reduces to the local case. All right. So so now I think we're prepared to state the Neron-Ogg-Shafarevich theorem, which we will do now. Okay, so theorem. So this is the Serre Tate version of the Neron-Ogg-Shafarevich theorem. It says that the following are equivalent for an abelian variety A over K, right? So it says that, so the first condition is that for all M in the natural numbers, which are co-prime to P, let's say M is not equal to 1, right? So that A M is unramified. Okay, and now I'm going to do some progressively weaker things. So this is saying that there exists an L, which is a rational prime, such that the inverse limit, so with L, so L is not equal to P, and this thing is unramified. The third thing is that there exists infinitely many M with which are co-prime to P such that this thing is unramified. Okay. So there's like 3 progressive versions of what it means to be unramified. So this is like at all places. This is all. This is for the L power. This turns out to be the same thing as L powers, and this is just saying that there's infinitely many. Okay. The 4th condition is that A has good reduction. Okay. So all right. And I guess the measure of how the ramification will tell you how bad the reduction is at a given prime. All right, so these are the ideas. So there's okay. So now I'm just gonna go ahead and start with the proof, and then I'll describe kind of what goes into the proofs, and then I'll start doing the proofs. Okay, so the first thing to do is to do 1 implies 2 implies 3. So this is the easy part. So the easy part is that, so it says that here, so this is unramified, if and only if, right? So this is the condition that you use, that for all n, right, a L to the n is unramified. Okay, so let's see. Okay, so I haven't said this. This is all over a field. Eventually, I'm gonna take this over to be over a ring of integers. So I'll tell you when I do that switch. It's okay. So let's just look at this. So this condition here. Okay, so this condition. So if we have this one, then we can get this one. So this is 1 implies 2. This one here is 2 implies 3. Okay, so so if we have this one, then if we have the Tate module is unramified, then it's going to be unramified for infinitely many m's, and m's can be arbitrarily large. So we have that. Okay, so these are these directions. This is kind of an exercise here. All right, so the 3 implies 4. So this is the hardest part. All right, and so this is saying that that the represent. So this is essentially saying something like AM. Okay, so that if it's unramified, which means that the inertia acts trivially, so that the stabilizer is everything. This is for M sufficiently large, right? So this implies that A has good reduction. Okay, and so let's do this. Well, okay, so A, K, K, K. Okay, this uses a lot of things, okay? The 4 implies 1, so this is the hardish part. This is not as hard. So this is saying that good reduction right, so this implies that here, so for all m coprime to p, right, that we have that the inertia acts trivially. Okay, so both of these need a description of this thing, right? So let me talk about. I don't know which one we want to talk about first, but so let me just say a little bit about these things, and then you can decide how much you want to watch, right? All right. So so this one here, so this one uses the structure. So this part here, this uses the structure of this. So the reduction of the torsion of the reduction. This is for the torsion of the reduction of the Neron model. It uses this description of the invariance, the torsion which is invariant under inertia, as the same thing as the torsion of the reduction, and it uses the so this Rosenlicht. So both of them go through Neron models. And then it uses a kind of a... So, okay, all of these things here are just to show that the reduction is proper. Right? So I guess I should remind you that there's... What do we need to show? So we need to show that the Neron model is an abelian scheme. And we need it to be proper. We need it to be a smooth group scheme over the base. And then we need the fibers to be geometrically connected. Okay? And then we do all this, and then we need, at the end of the day, we need a plus a transfer result. So to convert this, to transfer this properness into properness of the Neron model. And so this uses things like the Zariski connectedness theorem. Okay, this part down here, this hard-ish part, this just uses so let's do that. Let me just do this in a different color. So this just uses the structure of A bar M. No, actually, this doesn't use that. So this uses, sorry, nope, it just uses that AMI is the same thing as the reduction here. Okay, and this is the same thing as that we could take the maximal unramified extension of K, and then we could do these points as well. Okay, so all right, so let's do, so since these things are going to be used, let's do this easier part first, and then we'll do the hard part. Okay.